Can you hear me now? Yes? Can you make it? Okay, now? Can you hear me there in the last row? No? Not very well. Okay. Now? Can you hear me now? Yes? Okay. Welcome to my speech. It's going to be about system compromise detection on Windows system compromise detection. And just 2 hours ago, I saw a very nice presentation by two guys from Zonage, and I really liked what they concluded. They say that instead of building walls, it's good to have good ears. And actually, this is all about ears. This is all about having ears. So this is all about detecting that somebody is doing some stealth tricks on our system. I would like to say about three things today. One is new tool, System Virginity Verifier, as a tool which is intended to track the virginity of cut sections, in-memory cut sections. So this is a tool for rootkit detection. After we discuss this tool, I would like to say a few words about a new project which I started recently. It's an open methodology for compromise detection. I would like to explain what is it, why I think it's good to have such methodology, and we'll discuss things about it. And finally, I would like to say a few words about implementation-specific attacks, which are very, which started to be quite popular recently. And I will say something about that at the end of the presentation. Can you hear me now? From the beginning. Well, I forgot how it says it, but well, basically this presentation is about detecting Windows system compromises. That is detecting the stealth malware which is executing. Can you reduce this echo? Because there's a big echo. A little bit more silent. Okay, so about detecting this stealth malware on this operating system, and I said that I saw a nice presentation from Zonage, which ends with the sentence that it's better to have good ears than building walls. So this is about having ears. This presentation is about having ears. So detecting if our operating systems are really clean, because they might look like they're clean, but they are not. Okay, so today I would like to say about three subjects. One is System Virginity Verifier. It's a new tool for Windows compromise detection. This tool will be available on my website at the end of the week, or maybe tomorrow if I get access to internet. Well, this tool is verifies virginity of cut sections in mapped memory. It also allows for disinfection, so we can detect the malware and also we can remove the malware. And as it was a commercial project developed for some antivirus company, lots of efforts were taken not to generate false positives. Then I would like to say something about open methodology for compromise detection. What is it? Why I think it's necessary, and just a few things. And finally, a few words about implementation-specific attacks, which are quite popular recently. And basically, these are for example, the services which are sold by rootkit authors, like Hacker Defender author, the specific services which targets specific rootkit detector. And well, we'll say why it's important to address those things. Okay, we can divide system compromise detection efforts into three categories. One are based on integrity, verification of integrity of some operating system elements. These are tools like system files integrity, like antivirus tools, code sections integrity checkers like SUV, which I'm going to introduce you in just a few seconds, and other things. I will speak about it in a minute. So we have tools which check integrity of some operating system elements. So this is the explicit compromise detection, and we also have cross-view-based approaches, which bases on the fact that we have two methods implemented, like for example, two methods for listing the processes in the system. And one method is very deep, like it uses some very sophisticated method which bases on looking at internal kernel structures, and the other method is very simple. It just uses the standard API or just uses some standard system programs, and they just compare the results from both of them, and all the processes which were reported by the first method were marked as hidden. Rootkit Revealer is the example of this cross-view-based approach, or the Microsoft recent project Ghostbuster, Stranger Ghostbuster is also in this category. And finally, we got signature-based approaches, which are just scanning for known malware, and are very ineffective, of course. So today we are going to discuss this stuff. So the program which I'm giving you today, System Opportunity Verifier, is based on the very simple observation. All code sections of modules mapped into memory, like system DLLs or just the code sections. Code sections are read-only, right? Code is read-only. Most modern operating systems either forces, either recommends. The program cannot modify its code. Yeah, this is obvious, right? I would like to make sure that this is obvious for everyone. Like we have program. The program is compromises of code sections, data sections, and some other sections. And code sections should be read-only. So the idea, and of course, many rootkits, user mod rootkits, work by hooking code. So they make inline code hooking, and this inline code hooking, is just putting some jumps in front of the function products, for example. So the idea is very simple to catch all those rootkits. Just to compare all the in-memory mapped code sections with the corresponding sections in the corresponding PE files for the corresponding modules. So for example, we've got TCP/IP/sys module. This is the file. This is the file which is located somewhere in C/Windows/System32/drivers directory, and we also have memory. And somewhere in the kernel memory there is a module which is called TCP/IP/sys. So to make sure that nobody hooked code in this TCP/IP/sys module, we just compare the code section with the code section in the corresponding file on disk. If they are different, we have infection. If they are not, we have no infection of this class of rootkits. This sounds very simple, but we see that there are some problems. Of course, we shouldn't forget about doing fix-ups, so restart all the relocations, so that all the places where absolute addresses are referenced will be the same, because we are making byte-to-byte comparison. Is it clear, or should I go faster or slower? Is it too simple, or just okay? Okay. This idea, this is the very simple idea. I was speaking about this idea for years, and surprisingly, for years I have seen no tool to make this a code section comparison, or to make this code section verification. One tool which I was always using in the past, it was kernel debugger, and I was using check image command, which we will see in the demo just in a few minutes. And that's all. And that's funny, because this is one of the basic things which we should make sure that the code virginity is one of the first things we should make sure if we are talking about system compromise. System compromise detection. So this idea is very simple, but unfortunately it's not very simple when we start implementing it. First of all, rootkit technology, so-called rootkit technology, so in this case, inline code hooking. Inline code hooking is widely used by many other tools which are not rootkit. Tools like personal firewalls, behavior blocking systems, some monitoring tools like for example, well, some Kaspersky antivirus or whatever. System tracing tools like debug view or file monitor or many other tools which hook something in the LAS or maybe in the service descriptor table just to control the flow of execution. So because SVV, as I said, was a module for commercial antivirus system, we obviously need to take care of detecting the false positives and not report it as infections. So this is the one problem: how to deal with innocent hooking. So hooking by like this level tools. But first, another problem. Well, I noticed another problem which I didn't know about it before this, and this was self-modifying kernel in Windows. So as I said at the beginning, I said all code sections should be read-only, right? And this is a very obvious thing. Unfortunately, two core modules of Windows operating systems are exception from this rule. Those two modules are NTOS kernel, so the core kernel, and HowDLL. Maybe it's a good time for demo now. Can you switch the laptops? We got Windows XP here, but it doesn't really matter if it's Windows XP or Windows 2002 or Windows 2003. So this is command line, and this is can you see this? This is KD. This is kernel debugger. Try to make the phone bigger. Okay, can you see this now? Okay. So there's well-known check-init command, which we can use to verify well, particular module. Here it says 0 errors in module and there was kernel access. 0 errors means that kernel. Well, what KD just did? It just did the same thing which SVV is going to do. It just reads the end-use kernel exit from the file system, compares do some relocations, compare it with the module mapped in the memory, and says no differences. And we are happy because no differences. So code is read-only, and this is okay. Unfortunately, this is cheating, because if we use nospets option, which instructs kernel debugger not to filter out known kernel code self-modification, we can see that in fact there are 4 places in this kernel which were modified. Those errors means the code on the disk is different than the code in memory. Do you have an idea why Windows kernel does such thing? Anybody? I can read you the name of the functions. It's the name of the functions which body was modified. This is RTL prefetch memory non-temporal. The next function is key flash current TVE. Another one is KI system call exit branch. So this sounds like functions which deal with synchronization or some low-level stuff. And in fact, the reason for this is that Windows kernel adjusts to specific hardware which is run on and changes some part of the function to have better for speed, yeah, to be more effective. I was speaking with someone from Microsoft about this problem. Why is it done like this, and why isn't it possible to make a separate code section, let's say, well, alt text, for example, and put all the functions into the separate alt section, so it would be very, very easy to know that those modifications are just kernel modification, and these are not infection alarms. And the answer for this is, of course, the speed, because as he said, the kernel is optimized. The kernel code is optimized in such a way that it fits into specific caches. So the position of each function should be, well, like it is, and it would make an impact on effectivity if we move it to the other section. So, no matter if it's really true or not, we need to deal with this kernel modifications, because in other case we will make lots of false positives. No matter if it's really true or not, we need to deal with this kernel modifications, because in other case we will make lots of false positives. These are the modifications in HAL module, HAL DLL, hardware abstraction layer. We see a little bit more modifications. But the observation here, which is very, very useful, is that all modifications replaces nulls with somebody. So we can expect that these were the places left to be filled upon, well, execution. So it's easy to filter it out. Can you switch to the slides? So if you want to avoid HAL modifications, we can just make use of these observations. That if it's out to XX, then it's a kernel stuff modification. And it would be very difficult to write a rootkit, in my opinion, which would work by just modifying those files. Actually, it would be very difficult to write a rootkit which would work by modifying HAL section. And this is the reason why I don't check HAL section integrity in SVP. Although you can use the switch A to check all modules, but in default mode it's not checked. Anti-OS kernel is more problematic because it's a very important module from the rootkit point of view or backup point of view, and there are lots of stuff which can be altered by rootkit to I tested on many systems, are just not to something. So it's a 1 byte modifications. So this is pretty obvious because somebody put a knob just to mark that this may be modified in the future. And the rest are just modifications which are more than 1 byte long, are just the number of them is very little. And of course it's very difficult to write a rootkit which would, if not impossible, I think it's impossible, which would work by just 1 byte modifications, right? Okay, this was the demo which I showed you. Any questions up to this point? Is it clear or, yeah? Okay, now about innocent hooking. Not making alarms where there is antivirus monitor or something like this. So first we need to, I would like to define several types of hooking which you can observe in the system. But before this, just a small definition, what is missing and hidden files, what I mean by missing and hidden files. So file is missing when create files and this file returns error files. So the file is not present basically. And file is hidden when file first file or file next file on one of this file on one of the directory which contains this file fails. But in most cases, all hidden files are not missing. Is it clear? For example, if we install, well, Hacker Defender rootkit in a folder rooted, right? And so Hacker Defender will make it invisible, this folder, right? So if we list the C/directory, we will not see rooted folder. So find first file will not return this directory, right? But if we know the name of the magic directory, and if we try to execute create file on this path, it will succeed, right? So this is important to distinguish hidden and missing files. Any question? Anybody confused by this? Okay, typical innocent hooking is like this. This is the function which we hook. For example, this function might be kernel debug print function, and it will be hooked by debug v.sys module by sysinternals. If we use debug view by sysinternals, and it will just hook to some other function which will be in debug sys module or whatever. Or if we consider antivirus monitor, this could be, for example, I don't know, read file, right? Read file or create file, and it will transfer execution to the antivirus provided function. And the observation, this function will be located in a valid module, and this module will has corresponding image file which will not be missing nor hidden. Well, it's really obvious that the rootkit cannot use this type of hooking because rootkit is interested in hiding its file, so it will not be visible. Malicious hooking, this is what I just said. So this could be like this. We transfer execution to some module, but the module file is hidden, but it may be present. Debugger-like hooking. This is actually used by most of the tools like the system monitors from sysinternals. They have just one executable, well, like registry monitor, right? Red mode. Red mode consists of one module, one executable module. But when we run it, it extracts from its resource section. It extracts driver, rec something. And put it in Windows system32 drivers directory, loads it, and then deletes the file. So we have a situation when the hooker's code is in the valid module, and the corresponding image file is not hidden, but doesn't exist. Another malicious hooking. This is mostly used by more advanced rootkits. Again, we have a hooked function. Well, let's say it's registry rec key like registry key enumeration. It's hooked to the rootkit code, and the rootkit code does not belong to any module in memory. So if we traverse the list of loaded modules, we don't find the modules which has start and end address, which could contain this code. So again, this is an obvious sign of the malicious hooking. And to be complete, yet another possibility is that rootkit does not use simple hooking, because all those things, as you probably just noticed, requires that SVV or any other code integrity checker will resolve this code as a proper assembly, will disassemble properly. So the SVV can know the target address. If this is jump something, we need to decode the jump opcode, we need to add the address to the relative address and find the target address, right? But the rootkit can use some obfuscated code, like some polymorphic code, to make this jump, or can put the jump somewhere here, or, well, can make it obfuscated. So the code integrity verifier will not be able to decode the target address, right? And for example, recently I saw on rootkit.com an article how to bypass Vice. Vice is another integrity-based detector written by Jamie Butler, and it doesn't work like SVV. It doesn't compare code sections. It just searches for jumps at the function prologues, and if it finds a jump, it will report it as an infection. But so this author, which I don't remember, developed a technique to make it obfuscated, so Vice will not check it, will not find it. But in our case, this is not a problem for us, because if we detect code which we don't know how to resolve, which don't know how to decode, we just say, okay, this is malicious hooking, because I'm not aware of any antivirus monitor, neither any other intensive tool which would be interested in putting obfuscated code into the functions. It was this one. So this is the one which I was talking about. And even another thing which we should take care of is service descriptor table, or service table modifications. Service table, in many cases, is pointed by KI service table address, and this symbol is located, well, the address pointed by this symbol is located inside text section of entire kernel executors. So if we detect modification in KI service table, then we need to treat it in another way. We are not trying to resolve it as a jumping code, but just as an absolute address, right? The problem here is that not always, well, because the obvious way, of course, KI service table is not exported, right? Because this KI is a kernel internal symbol. So the obvious way from finding a service table is this expression, right? This is KE service descriptor table, which is exported, of course, which binds to the service descriptor table, and first element and first field of this element is just a pointer to this. Well, it's just a pointer to the service table which is currently used by the system. I hope everybody knows this. Well, this is obvious, right? Or not? If anybody have some experience with SDT rootkits? No? Okay, so, well, basically, KI service table could be, in most cases, found by this expression. But not always, as it turned out, because, well, some antivirus monitors, like Kaspersky Antivirus, use their own service table, so they modify it to point to their own service table, so we don't know where KI service table is. And a guy called 210, well, several months ago, published article on rootkit.com about how to find it in a very smart way. So this is the way SVV is uses here. Okay, finally, before the SVV demo. Oh, this, I think the red cable is not connected well. Because this is red and this is more red. Like, well, it's just more red. If it was connected good, you would see this. So this the SVV on the output gives one of the 6 verdicts. It could be, well, this is green. This is green. This should be green. This should be yellow. This should be orange. this should be red and this should be deep red. Can you do something with this color? Oh, yeah. Okay. Now, so you saw all the presentations with red colors. Okay, so we can start again. Okay, so we can get blue verdict, which means that there are not single modifications, not even those modifications which I showed you, not even kernel self modifications. Of course, this never occurs in the wild, but I just added for the completeness. Funny thing is that SVV gives you opportunity to disinfect system, and you can specify to which verdict level, to which level you would like to disinfect. So this is 0, and you can specify that you want to disinfect to level 0. So you can make your system 100% virgin, and it still works. I tried for several hours, and it worked like before. So. Green. Okay, this should be more green, but okay, this is green, let's say, and this is the most typical verdict, it means that the system is okay. Yellow, this is the innocent hooking detected, one of the hooking which I just described you. Orange, this is orange, not brown. But this is orange, and it means, well, less innocent hooking detected. In most cases, it means debugger like hooking detected. Those hooking with missing files, with missing files in system 32 drivers directory. Red means it's very likely that we have something in the system, and deep red is, well, 99.9% that the system is compromised. Okay, then can you switch to this? So let's start with some simple key. Yeah, I should have done that before because this laptop has only 500 megabytes, and this is really too not enough for the machine. Hopefully, we'll reach this state. Any questions in the meantime? Any questions? Maybe? Okay, so we have this is the system with Vanquish rootkit installed on it. Come on, maybe some questions. In the meantime, I need to change this font. And, well.
I have a quick question.
Okay.
So,
who are you? Where are you?
Hi.
Okay.
So, I think what you're doing, and I just want to try to understand a little better. I think what you're doing is you're going to run the system virginity verifier against a system that we're going to see as compromised. Is that right?
Yep.
So, can you tell us ahead of time what the results are going to be and what you're going to be able to restore to, or is that a part of them? I'm just trying to understand
what the results will be if I
exactly what level of compromise are you going to detect here as you're running the verifier in this instance?
What level I'm going to set the...
So you showed us the spectrum of the different colors for the different levels of compromise.
It will show on the command line.
So the command line will return the level of compromise?
Yeah.
Okay.
This is here we have one visual key, and I will just change the font so that you can better see it. And we will see, for example, red. Well, we see only the name, right? Because I don't know how to color some text. So, well, maybe we don't know what's on the system. I can tell you in secret that here we have one visual kit. But we don't need to know it. We just run SVP. Can you hear? Can you see this? This is SVP check, right? So yeah, it's really slow. Warming up, maybe see something why it's here. Now verifying auto modules, kernel and system levels, and here system infection level 5, deep red. Okay, we can now see some more details about it by putting /m switch, which will show the modifications. Oh, let's say this one. Modification at address 77E279. This is function enum services status. This function was obtained by reading export table. Oh, this is inside some module which is printed up. I don't want to scroll that. And jumping code was detected. Target address was 1AE something. This address is inside module. We don't know the name. There's no name for this module, which is in this range. And module file is not present. And I think it should be also hidden, but displayed here. Let me see this. Here we see the CentOS kernel modifications, those modifications which we expect. You can see at the every modification verdict level for this modification. This is 1111, so green. And then we see kernel 32. So we see some modification in kernel 32 driver, DLL, kernel 32, and we have modifications inside load library, create process. And this is a mistake of this output function here, because this should mark the file as hidden, not present, because it puts the verdict 5 here. But well, the logic works well, so we have verdict 5. So the total system verdict is the maximum of the verdicts of the single little verdicts. Okay, maybe let's see another rootkit like Hyper Defender, which is the most advanced of them, and we'll see how disinfection works on this rootkit, just to save time. Okay, the person who asked the question just a few minutes ago, does it answer your questions, or you still have some questions?
That makes it much clearer what's going on. I was just trying to get a little more on.
So do you talk to the Hacker Defender author?
Did I what?
Do you talk to, do you trade email with the
Oh, no, I didn't report this as a vulnerability or something like this. Okay, I need to change the phone, I'm sorry for this. So again, this system looks normal. Well, you need to believe me that it looks normal, because we don't have time to check if it looks normal. I'm sorry for this long list. We don't have questions. Maybe somebody lost and wants some explanation. Okay, so again, we have a system, well, we don't know anything about it. So again, we will start this VB. Warming up is just a delay loop. It's because some rootkits is to give some rootkits time to infect the detector. Okay. Again, we have some infections in some system DLLs. Again, we have deep red, and again, let's see at the modifications. Again, we have error service status function hooked. This is not a surprise because many rootkits are interested in hiding their own services, so we cannot see them in control panel services, right? So this is the function which is responsible for returning the services running to the computer. So many rootkits, simple rootkits, hook it, because more clever rootkits, well, does it in a different way. Again, we have a jumping code elected here. Oh, we can. This is the expected code, and these are the bytes which are observed in the memory. E9, everybody who knows assembler knows what E9 is. Yes? Anybody knows what the E9 opcode is for?
No.
Yep. It's a relative jump, as Dave said, and this is the relative offset, so this is the jump code, and this is the decoded target address, and this target offset doesn't belong to any module, which is innocent hooking type 3 or something like this, or 2, I don't remember, and this is obviously very suspicious, so we have deep red alert. So let's see how the disinfection process works here. Well, let's see. I'm not sure if I have Process Explorer on this machine. Yeah, okay. We have Process Explorer. Oh, we have services here. Hopefully you can see this. Well, there are nothing suspicious here. Let's run the disinfection process here. And we'll watch the Process Explorer. From the sure. And now we see Hacker Defender appear here. What SAP just did, it just restored all the code modifications which are marked as infection level 2 or more, and it restored it, so the functions are not hooked yet. Not hooked anymore. So Process Explorer now gets the real system view. Is it clear? And we can also go to the main directory, for example, and do direct. And now we can see hides the directory which was hidden before. Maybe you can show. Yeah, it was. This is the directory I did at the just at the beginning. There was no hide stuff. After disinfection process, everything is visible. And now, of course, to remove the rootkit from the system forever, we need some antivirus approach to scan the registry and to remove the services. Okay, let's see how SEV behaves on a clean system. Any questions? Yes?
So how is SVB actually fixing that? What calls are you making?
Well, SVB has client-server architecture. It has its own kernel agent. It has its own module in the kernel. This kernel restores the memory by just writing to the memory because it's in ring 0, so we can write to the memory. Yeah. So the restoration process is consists of 3 phases. First phase is first stage is to restore kernel modules. Then we restore our own process modules, and we don't need any API for this because we can just unprotect the code section of our own process, and we can just write to the places which are altered. Then, when we have clean kernel and clean code in the user mode for this only process, now we can use API for accessing other process memory. API like open process and write process memory or something like this. And then at the end we repair other processes in the system. Okay, let's see how it works on the clean system and what happens when I run regmon, for example, here, registry monitor. It's punishing next. As we check things, warming up, verifying module and modules. Okay, and level green, infection level green. Let's run. This is registry monitor. Let's see how it looks now. We got orange. Orange because registry monitor is as a tool which puts only temporary file in system32 drivers directory, loads it, and then deletes the file. So well, it might be some very simple rootkey, but it's more chances that this is a system tracing tool. In a commercial product, it's solved like this. It should be solved by just displaying a message to the user that maybe he or she is using some system tracing tool, and he or she is kindly asked to disable them and rerun the test, and if the user doesn't know what the system tracing tool is, then it means that he or she has the virus or something like this. Let's get rid of this registry monitor. Oh, we can see this registry monitor. It constantly monitors all the registry references. Now, when I disinfect the system, well, the registry monitor is disabled. It doesn't work. It doesn't work. Okay, I can do something like normally pushing start button in Windows would result in thousands of registry keys read per second. And just for the end, let's see how 100% virgin system looks like. T says to which infection level we start the system, and I will put 0 here. So we will restart our kernel self-modification and see that the system will still work, hopefully. Okay. We can run again. Run the CD again. And now we can see the verdict level blue. Not a single kernel modification is not present in the system, but we can see that the system still works. Okay, can you switch back to the slides? Okay, this is the tool I'm giving you tomorrow or at the end of the week. It has two problems. One problem was discovered on Sunday. Well, SVB crashes when run on terminal services, when terminal services are enabled and there are more than one user login. And I didn't have time to look at this problem. And another I discovered it online, and it was the problem that it's not a problem, it's not a bug, it's it's a feature which should be added to SVV to make it more complete. Because SVV verifies only .text sections, which I believed will be enough to catch all the rootkits, and it probably is enough to catch all the code modifying rootkits, but it didn't catch some backdoors like EI root boot backdoor. Anybody heard about EI root boot backdoor? It was presented on Black Hat a few months ago, and this is quite funny backdoor. It's more backdoor than rootkit, but it modifies Andy's driver. It hooks something in Andy's driver, and the code which is hooked is inside page sections. So another feature which should be added shortly to SVV is to check not only the text sections but all sections which are readable and not writable, which are code and not writable. SVV is very SVV takes care only about code virginity. There are many other ways to write rootkits or backdoors in such a way that they will not modify code sections. You can have such simple rootkit or backdoor rootkit which modify SDT, service descriptor table, or we can have such sophisticated rootkit which modifies IRP, interrupt request packet tables in subdrivers, or a rootkit which does some interesting tricks with configuration manager module, the registry management module. So there are quite a lot of techniques to write rootkits which doesn't involve code modifications. Unfortunately, I observe lots of rootkits and backdoors in the wild, which are very simple rootkits which do modify code sections. So SVV is targeted only to detect those simple rootkits. SVV 1.0. Next version should of course include verification of other system components like export, import address table, TLS, SDT, ITT, IRP tables, which I said just a second ago, and these pointers to get some backdoors and cover channels in kernel, and more. And now you should have the feeling that, well, you should ask yourself now, I hope you're doing it now, that, okay, I said that code verification is necessary, right? We also need to verify IAT, import address table, and other objects in the system. So the question is, how many other objects can we list? Right? How many other objects can we define which SVV should check, or any other verification tool? So we need to define all the vital operating systems, operating OS components, which are vital. I mean, which are vital in the sense that if they are changed, it means system compromise. And this is the idea for the OMCD project, Open Methodology for Compromise Detection. But this is the project which just basically, which is for Windows system, and it's going to be like this, and this are vital system components, should be verified in this one. Quite easy to bypass, as a recent article on wiki.com showed, for example. SDT restore by skchunk, which is a tool targeted only at verifying SDT table. Well, this is another vital system component which should be verified. Captain Hook is a not public tool. It was sent to me by Chris Keller when he saw SVV, and it's very similar to SVV, with the exception that it doesn't care about kernel self-modification nor about detecting innocent hooking. So it seems rather like a proof of concept tool. I sort by Mr. Ru's PGF USDC, whoever he or she is. This tool is not really a integrity verifier. It's more enumeration tool because it allows to see SDK contents, Winter-v2 hooks, all the assets, hidden processes, etc. And the user needs to judge by herself if it's if it's a suspicious notification or if the content is suspicious or not. What is the comparison of those tools? As said, SV10 is only targeted at code verification at the moment. Of course, in the future it should extend to the other areas. Any questions? Any questions? Because we are going to the second part, which will be very short, as well as the third part, which will be very short. So just to make sure you ask all the questions. Can I have some water? Okay, any questions? Open methodology for compromise detection was born when I was doing SVB, and this is hosted by ISACOM, Institute for Security and Open Methodologies, which is known for a project which is called Open Methodology for Security. Well, OSSM, something like this. Probably anybody heard about this? It's open. OCM. Oh, SSA. Huh? Okay, anyway, this project was led by me, currently focused on Windows system, hosted at ICCOM, and the goal is to create a list of all important OS elements which should be verified to find system compromise. And it's not only a list of objects, but also I hope that it will contain some methodology, some algorithm, how this should be checked. So, for example, this will discuss problems with innocent hookings and kernel self-notification when it will mention code verification. It's intended mainly for developers of other compromise detection tools, and I hope it could be useful for reference as a reference if we are comparing different tools. Like we can say that our tool implements section A, B, C, and D of this OSD implementation. And I believe that, in contrast to what many other people say, that there are only finite number of ways in which the rootkit or backdoor or cover channel or keystroke logger can be implemented in the operating system. Like if we say we should verify code, ITT, SDT, IRP tables, and the likes. After some time, if we make this list complete, well, the more complete the list will be, the less space for the malware will be in the system, and hopefully this will close some. Well, otherwise, how it's going to be created. This is the OSD outline. Let's start with some definitions. Then we have file system verification, which is a very simple things like making sure that the system files are not infected by checking PE files, signatures, digital signatures, and things like that. Registry verification by checking that. These points are to make sure that there are no simple user mod rootkits which could be easily detected. Well, with a simple methods, because we can concentrate on very sophisticated detection methods in kernel, somewhere in kernel, but somebody can install very simple user mod process which will not implement any hiding or something like this, and will not detect it. So just to make sure that no one will say, well, I believe that there are so many methods for implementing rootkits in user mode that is not necessary to go into kernel. So those points are intended to catch those simple user mode rootkits. Then we have user mode level memory verification and kernel mode level memory verification, which I'm going to discuss in the next 2 slides, and network activity analysis, because I hope that this methodology will because all the first points are dedicated only to operating system, are host-based. And the last point is network activity analysis, so how to discover, well, some backdoors or some covered channels by analyzing network traffic from Windows machine. So this is from the other point of view. Okay, section E. These are just proposed, well, some things which I just thinking about what to put in this section. This is still under development, so we can add some other things here. First, we have discovering suspected but not hidden processes and threats to find out all those simple user mode rootkits too. Cross-section verification on user mode level, so this is what SVV does also. And